So the talk here on planetary resources is entitled Harvesting Asteroids to Fuel Human Exploration and Prosperity. So in the format that's been laid out for us, we'll begin with the huge problem. But first, a quote that I love by Konstantin Tsiolkovsky, the founder of cosmonautics, that the Earth is the cradle of humanity, but humankind cannot stay in the cradle forever. So as we speak about huge problems, the problems that we're taking on here, that we're speaking about, that we're passionate about, are threefold. First of all, that it's during our lifetime that the human race is moving irreversibly off the planet. That in fact, we have a moral obligation to become a multiplanetary species, to back up the biosphere so that no natural disaster or man-made disaster can ever wipe out all that we have created. Second, that driving continued exploration is critical. We as a species do our very best work when we are exploring. We are driven to explore, and as we explore, we drive breakthroughs. We are the best that we can. But ultimately, exploration funded by governments starts and stops and starts and cancels. Think about the fact that from the Trieste 50 years ago, we went no place until James Cameron went down to the ocean floor. And we haven't been back to the moon in 40 years. It's only literally when we have what I call exothermic economic reactions, exploration driven by making money, that we are able to really have consistent long-term exploration. And exploration looking for resources is what's fueled humanity to go from the new world, from the old world to the new world, and from the new world to the West Coast, and literally driven us over and over again. And finally, the notion of the problem of literally not constraining ourselves to the resources we have here on Earth. That we can expand the resource base of humanity, and that everything we hold of value on this planet, metals, minerals, energy, real estate, fuel, the things we fight wars over, are literally in near infinite quantities in our solar system. The Earth is a crumb in a supermarket filled with resources. So, our radical solution? None other than to identify, prospect, and mine near-Earth asteroids for fuels and precious metals. So, why near-Earth asteroids? As it turns out, we are living in a solar system that is flooded by asteroids, rocks from single meters to hundreds of kilometers in size. And so what I have on this graphic here is a representation of, if you see Jupiter, Mars, Venus, and Earth, and the asteroids as they were 15 years ago in 1997. And what we've learned and discovered is a huge amount of asteroids. So let's begin the simulation. It's actually a data representation. We start in 1997, and every time you see a flash here, it's a new data set being added to our understanding of what's in our solar system. The large cluster you see are, in fact, the main belt asteroids. But we go from 33,000 in 1997 to literally 600,000 this year. And that giant concentration of asteroids near the main belt, a small percentage of them come very close to the Earth from an energetic and a physical distance. So a few of those stats. In the solar system, we have about 1.5 million 1 kilometer or larger asteroids. In the near-Earth space, again, relatively from an energetic and physical standpoint, we've got 981 known 1 kilometer size asteroids that come very close to the Earth. If you expand that to 100 meter class, we've got just over 20,000. Now here's the key point. Of this population of asteroids, some 17% of them are energetically closer than getting to the surface of the moon. In fact, if you include the round-trip energy cost, nearly 50% of them are closer than getting to the moon and back. So we're interested in actually three particular classes of asteroids. The first are what are called carbonaceous chondrites. These are, think of them as dirty ice balls, 20% water and volatiles, hydrogen, oxygen, nitrogen, and carbon, methane, water. Now what's interesting about these, if you can literally bag these literally bag them, and use the sun's energy to take that water out and recondense it into fuel. A 75-meter carbonaceous chondrite asteroid has enough hydrogen and oxygen to have fueled all 135 spatial missions. Incredible. The other class of asteroids, the second of the three I'm interested in, is LL chondrites. These are asteroids that are rich in platinum group metals. Literally, rubidium and palladium, osmium, iridium, platinum. And the numbers here are themselves amazing. One 500-meter LL chondrite nickel iron asteroid has more platinum than has ever been mined in the history of humanity. And we have 2,500 of these in the 500 class that come near the Earth. So why are these of interest to us from a mining standpoint? Well, as it turns out, the Earth, when it was formed, all of the iron-loving, the siderophile metals, the PGMs, literally sank to the center of the Earth. And they sank there because of differential gravitational settling. But literally, the crust of the Earth is rich in the light metals, like aluminum. When we go and mine platinum in places like South Africa and China, those are sites of previous asteroid impact sites. So when you go to the asteroids themselves, we literally have concentrations of platinum and these platinum group metals that are hundreds to 1,000-fold more concentrated than the best mines on Earth. So here's just one example of an LL chondrite. The name rolls off the tongue, 2011 UW-158, and onto the floor. But this is an asteroid that's known. It's a target for us that we're interested in. It's a half a kilometer by kilometer in size. You can see it literally going outside of the Earth's orbit and coming close to the Earth every 1.9 years. So it means there's a launch opportunity to reach this asteroid every 1.9 years. And it takes about 0.7 years, 8 months to get to it. Here's the kicker. This asteroid has a net value of somewhere between $300 billion and $5 trillion. Now, of course, if you bring back that much platinum, it's going to sort of depress the market. So our financing plan is actually we're going to buy puts on the platinum market, announce the mission, finance it, and go. So the third category of asteroids, not our business, but of interest to us, are Earth impactors. So on a regular basis, every 100 years or so, there is an asteroid that impacts the Earth. And one of the consequences of being able to have an industry that's going out to mine asteroids is our ability to actually protect the Earth should one be coming at us. Now, we didn't arrange this, but next week on February 15th, there is an asteroid, 2012 DA14, that is coming within 14,000 miles of the Earth's surface, well within the geostationary belt, 45 meters in size. And this asteroid is the same size as the Tunguska asteroid that hit 100 years ago with the impact of 1,000 Hiroshima bombs. So if that asteroid was literally 14,000 miles closer, which is insignificant if you would on these types of levels, it would be huge. And if that asteroid 100 years ago hit any place other than the middle of the Kazakhstan, the Ukraine, it would have done tremendous damage and cost millions of lives. So the question is, do we think this is doable on an engineering scale? And the answer is absolutely yes. And I'll use one example to show how we think about this. So I've gotten to know the executives at Shell very well. They're the sponsor of exploration at the X Prize Foundation. And the head of exploration there explained to me how literally, in the 70s and early 80s, the deepest the oil wells ever went was 100 feet of water, because that's what humans could do. And in the early 80s, Shell discovered a large, massive oil reserve off in the Gulf of Mexico. And it was 5,000 feet below the water surface and 5,000 feet below the ocean floor. And they had no idea how to get to it. But literally, the value was so incredibly huge that they invested $1 billion to figure out how to get access to that oil. And today, the average oil field development runs from $5 billion to as much as $50 billion. When the value is high enough, the technology can be built. So I'll end my portion on this slide is to say that the phases of asteroid mining are the same that we have here on Earth for regular mining. Detect the asset, prospect it, claim it, mine it, and then return the materials to the point of need. I'd like to introduce my partner, Eric Anderson. Eric?
Thanks, buddy. Okay. Well, hope you're enjoying this discussion on asteroids. I'm going to talk to you a little bit more about the technology and how actually we're going to be starting off and really doing this here over the next few years. Okay, so as we talk about asteroid mining, what sounded like science fiction to actually turn it into science fact, we really sat down and thought to ourselves, what are the requirements? What are essentially the system requirements that we as a company, Planetary Resources, would need to have in order to develop technology to make this viable? What kinds of spacecraft, what kind of systems would be required, and what would the characteristics of those systems be in order to actually make this possible? And so the first one is clearly something that popped right out, which is that we cannot be dependent on government. This cannot be subject to the vagaries of NASA or the Congress's wishes on what they'd like to spend money on, so certainly not for funding, but also not for infrastructure. We cannot depend on NASA. We cannot depend on the Deep Space Network, and so we are going to have to build a system that can stand on its own two legs commercially, from an infrastructure point of view, from a technology point of view. Number two, we need to be able to produce spacecraft every year, numbering in the hundreds, okay, eventually thousands, not one per year. Today, and for the past couple of decades, certainly, building a rocket or a spacecraft has been like creating a piece of art. It has been something that is the furthest from mass production that I can think of. Okay, and we need to take that and just flip it over, completely over. Number three, we need to create systems that are as close to possible, or as close as possible in cost, in terms of going out and prospecting and gathering data as is doable, commensurate with what the mining industry and the resource industry is used to today. Okay, instead of spending $2 billion or in the case of, for example, the Japanese asteroid sample return mission that spent a couple $100 million to bring back a couple of grains of dust from an asteroid, we need to be able to go and prospect and understand the resolutions of these asteroids down to millimeters and to lay a claim of ownership for tens of millions of dollars. And this is totally doable, but this is a requirement that we have. And we're able to do that through the mass production and the systems we're going to talk about. And the fourth one, perhaps the biggest one and the most important for the future, is to turn asteroid mining into an information technology to the greatest degree possible. I know that sounds crazy, but we can do that, and we'll explain how that's done. Okay, so those requirements lead us to design architectures that have also certain key characteristics. Well, what are those characteristics? So number one, if we're going to be building hundreds of spacecraft per year, we need to have small, highly reliable spacecraft. Very low cost, yet very high performance. And so you've got to build them small. This guy right here, which we're going to show you in a few minutes, that is the actual size of a spacecraft that is going to go and prospect for asteroids. So number two, we need to make very intelligent use of subsystems. We need to double up and triple up on the systems that traditionally have had their own space, no pun intended. And I'll show you what that means. But there's no reason for us to have a unique comm system if we can also use that same infrastructure and that same system for something else. Number three, we need to use laser communications. Okay? As you know, the size of an antenna is dependent upon the wavelength. It's proportional to the wavelength. And the smaller you get the wavelength, the smaller the antenna can be. And so it doesn't do us much good to build a spacecraft like this if we've got to send it 30 million miles away and it's got a 30-meter antenna hanging off of it. It's just not going to do it. So laser communications is something we have to develop. Number four, we need to make the most up-to-date, state-of-the-art use of autonomous systems, artificial intelligence, software, machine learning, all of those things. We need to pack into this little guy right here the intelligence that is required to not just take pictures and bring us data, but actually give us the answer. Send us the answer. And we'll talk about that. And number five, again, going right along the line with with turning asteroid mining into an information technology is we want to get as many of the technologies we're going to use in spacecraft onto exponential growth, onto systems that are subject to Moore's law or a law like that. For example, radically increasing battery storage production versus cost and things like that. So we're going to put all of these key characteristics in terms of architecture into the design for this guy. So what are these guys? Slight aside, this is the Arcid series of spacecraft. We start with the Arcid 100, and the Arcid 300 is a grouping of Arcid 100s that have deep space propulsion, deep space communication, and are going in a swarm to characterize an asteroid. But before I jump into that, I just take 30 seconds and tell you where Arcid comes from. So how many Star Wars fans do we have in the crowd? Okay, I would hope to see everybody's hand go up, but that's all right. So mostly everybody. So the thing that is closest to what the Arcids are in Star Wars would have to be, of course, the Imperial probe droids. Now, for those of you who are true Star Wars geeks, like Peter and I, you would know that the Imperial probe droids were built by a company called Aracid Systems. And, of course, the Aracid Systems was based on Coruscant, and they built these droids that went out into the galaxy and looked around and got all kinds of data and sent it back. Well, Arcid is named in honor of Aracid Systems, and so yes, that is in fact proof that we are true geeks, and thought I'd throw that one out there for the Star Wars fans. Okay, let's talk about where we were as an industry just 15 years ago. So what you see right here is a picture of Landsat 7. Landsat 7 was an $800 million spacecraft. And for that $800 million, you got 15-meter resolution. That's 15 meter basically per pixel, okay? Not bad for 1997, but I mean, literally 2 or 3 orders of magnitude worse in cost performance than we're going to show you today. Okay, what was the state of the art just 5 years ago? This is a commercial project. This was financed commercially, so we can't even attribute part of the inefficiency to the government work there. This was financed commercially. A project called RapidEye, 2007, $40 million cost for a satellite. It was able to be to bring the resolution up by a factor of almost 3. And so overall, you know, a couple orders of magnitude almost improvement on cost performance. But here we are today. So 2013, the Arcid 100 for $4 million. This guy is almost 1,000 times better, 100 to 1,000 times better than what we could do 15 years ago. And we need to keep that price performance curve going. This is what's going to make asteroid mining possible. This technology improvement and using this spacecraft bus as the method for us to go explore the solar system. Okay, let me introduce also, through the photograph, Chris Lewicki. So Chris Lewicki is the president and chief engineer of Planetary, and he was one of the top people at Jet Propulsion Lab and was a mission manager on 3 of the last 4 Mars missions before he came to us right as the most recent mission was landing, and basically brought with him 6 of the best people at JPL. So we have a wonderful team of people. And why don't we pull back the sheet on the Arcid 100 here. We like to call the Arcid 100 the smartphone of spacecraft. So, and it actually makes a lot of sense. You can pull back the solar panels. The optic, we'll lift the optic here. This is a deployable optic. This guy can get us down to 1 meter, 2 meter resolution from an orbital altitude, by the way. You know, you'll notice that the two spacecraft I showed before are actually Earth observation spacecraft. And even though this guy is intended to analyze asteroids and will do a really good job at it, we're getting a lot of interest from Earth observation customers. You know, for $4 million, you could launch a constellation of 5 or 10 of these if you're a company, you know, a mining company on Earth, for example, and really have an incredible ability to survey and gather intelligence on land today for what would have cost billions of dollars just a decade ago. Anyway, we like to call this the smartphone of spacecraft because it very much is in line with the evolution of smartphones. You know, 50 years ago, mainframe computers, they basically, you had a room or part of a room for a subsystem. You know, you had the disk drives and the vacuum tubes and the punch cards and all this kind of stuff. It was huge, okay? And then eventually, over the last 15 or so years, you evolved to the point where you could have a laptop and different subsystems, but at least they were packed on a little briefcase-sized thing that you could use and take with you. And now with smartphones, all of those same systems are not only on the same little box, but they're on the same card. They're essentially all one system. And so the camera that you use to take photos of your daughter's birthday is the same camera that you can use to look at the mole on your arm, or to figure out where you are matching up to a map, or whatever. The systems and the sensors are the same. You double, triple up on the systems. And that's what we're doing with this spacecraft right here. That's the key to doing it low cost and high repetition. Example. We'll give you 2 examples of that, then we'll move on. This optic is an optic that can give you very high performance in terms of resolution. So when we're a kilometer or 2 from an asteroid and orbiting the asteroid, dwelling on the asteroid, we can get millimeter resolution. From Earth orbit, we can get 1 or 2 meter resolution. Okay? But why would we waste that nice optical space? We're going to use that same optical chamber for communications. And if we're doing optical comm using lasers, we can actually make double use of that space. Okay? That's what I mean by doubling up on systems. Very important, saves a lot of mass, very, very, very important for our system in the future. Another example, we actually use the framework, the skeleton of the spacecraft as the propulsion tanks. Okay? There's another place where you do that. It's called aviation. Okay, the Boeing 777, the 787, you'll find the fuel in the wings and the little nooks and crannies, because why are you going to waste that space if you don't have to? If you look at a traditional satellite, you'll find a big bus, and it's got the skeleton there, and you'll see these big spherical tanks sort of plopped off to the side in a totally inconvenient location. So why do you need that? You don't. You have to design for multiple systems, really make use of every last cubic centimeter of space to make it cost effective. Okay. There are a bunch of other technologies. Afterwards, if you'd like to come and mill around, we can show you all the little nooks and crannies and pull back the blanket, and there's all kinds of great stuff in here. But just to give you 3 more of some of our favorites. So number 1, we are using carbon nanotubes for wiring and for thermal paths. Now, for those of us in the space industry, you've heard carbon nanotubes for like decades. Oh, we're going to build space elevators that have carbon nanotubes. We're going to do this with, you know what? Carbon nanotubes have been as close to unobtainium as possible in the space industry. But they're real. We're going to use them. This spacecraft, when it launches in 2 years, will be using carbon nanotubes. Number 2, autonomous diagnostics, target characterization, autonomous target characterization as well. What that means is that there is going to be as much intelligence on this vehicle as possible. We literally are going to send back the answer. We're not going to just send back the data. Part of the reason why we've been so limited on our deep space scientific missions over the years is because we're sending back every pixel of data. The computer can't do any of the calculation on board, or if it could, they didn't program it that way because it was too risky. So in terms of spacecraft diagnostics, going to an asteroid and sending us back the 3D file send us the file that is the asteroid. What is the spin rate? What is the debris cloud? What is the albedo? What is the characterization of the materials on it? All of those things coming back as the actual answer. And the third is just to build them in a swarm. The concept of distributed computing, that is what we do, distributed spacecraft. There's lots of reasons for that. I won't go into it right now. I can certainly talk to you about it later, but it makes perfect sense. You take so much risk out of the system when you don't spend the last, the 50% of the cost going in to try to reduce the last 2% of risk of a spacecraft. You don't need to reduce the last 2% of risk if you take 7 of them, because you can afford to lose 1 or 2 and you still have perfect mission success. Anyway, this is an Arcade 100 and its mission. So the first mission for the Arcade 100 is to go to orbit and take the list of top 20 or 30 asteroids that we are most interested in right now. So as Peter mentioned, there's actually about 10,000 near-Earth asteroids that have been discovered. That pales in comparison to the millions in the asteroid belt, but there are 10,000 that have been discovered already. And we've got our little hot list of 20 or 30. But by sending 2 or 3 or 4 of these Arcade 100s into strategic orbits, we can take that list and really understand what the best ones are to go after for the Arcade 300 missions. So we're going to send 20 or 30 swarm missions out there over the next decade. And that brings us to the Arcade 300. The Arcade 100 is going to space to tell us where to send the Arcade 300s. And the Arcade 300s are going to go in a swarm. They will be, as I said, the distributed computing platform of the future for space. Each one of them can serve the function of all the other ones. So they are autonomous, they are intelligent, and they can do each other's jobs. They're going to communicate over essentially a local area network, and they'll bring us the answer. After, by the way, the most important part of an Arcad 300 mission, beyond the data, is to actually make the claim of ownership, of whatever form that takes. Right now, the law says we can go and take resources from space and use them. Their law needs further definition. For example, if we go to a target, we want to be able to have exclusive rights to that target if we do something there, if we perfect our right, if we plant a flag or a beacon. Okay, that right does not exist yet. But as we develop the frameworks for that on an international level, then this will become important to go and not only characterize it, but plant that flag. So when we come back there to do the mining, it's all set to go. Now let's talk about the mining, because this is where a lot of people really get their imagination pushed up against a wall, so to speak. This is tough. But the beautiful thing about this is there are no laws of physics that prevent mining asteroids. It all comes down to economics. Okay? And what we can tell you about the work we've done already for mining asteroids is really, really positive. Let's think about the first principles. Okay? First of all, we have an unlimited energy source in space. The sun, we got 1.3 kilowatts per meter squared at a distance of 1 AU, 93 million miles. We have that 24 hours a day, 365 days a year. If we get a little bit closer to the sun, we have more. If we get a little bit further, we have a little bit less. But it's always there. And the sun, it turns out to be really useful when you're doing mining. Number two, the fact that we don't have people, it's all robotic, that's a feature, not a bug. We want that. The two largest costs of terrestrial mining are manpower, it's the people behind it, and energy. And boy, does it take a lot of energy. So we have these things for free in space, okay? And with the sun powering, just for example, a 1 kilometer array, we're going to end up being able to take a typical platinum-rich asteroid, so let's say one that's less than a kilometer in size, and just by heating it up, okay, by the way, the platinum group metals have some of the highest melting points on the periodic table. There's literally, the platinum groups are like, 5 out of the 7 hottest, the highest in terms of melting point, and nothing else on the asteroid even comes close. So we can melt away the other elements, leaving only the platinum group metals, and by doing so, one asteroid, 5 times the world output in platinum can be created using only one asteroid. That's pretty amazing. All right, then the real stretch for the imagination, a lot of people worry about, is how do we get this stuff back? Okay, this is really, this is hard, okay? But I'm not even going to talk about the first two, because the first two are things we know how to do. This is bringing stuff back in a capsule. Check, done that for almost 50 years. Inflatable decelerators, essentially the same thing. It's just it's a balut that you open up and you get that same ballistic surface. Things like the space shuttle, things like return capsules, things like even a space station can be controlled in its descent. It's happened many times, it'll happen many times in the future. But what about really stretching it and making it so that we can do this even more efficiently, even more safely, and with even less cost? That's where this metal foam comes in. So we've done a lot of research in this area now and gone back and looked at the science. Platinum, for example, at 23 grams per centimeter cubed is an extremely dense material. But if you can take that platinum and turn it into a foam using basically heat, well, we have a lot of that up there, you can actually turn 100 kilograms of platinum, as it says right here, into a 2-meter diameter ball. It has basically the aerodynamic characteristics of a wiffle ball, okay? So can you imagine this stream of balls being re-entered, into a desert somewhere where, by the way, your area ellipse and error ellipse on re-entry is going to be about a kilometer max. So if you put it into a desert or some area like that, you're literally going to have riches raining from heaven, and this is totally doable. Of course, it's hard, but allow that in your imagination. It's totally possible. Okay. What I'd like to do now, Peter, is to have you come up and conclude. And I don't know if we're going to have time for questions or not, but this is asteroid mining.
Thank you, Eric. I'll mention one point that Eric didn't make on the last slide, which I think is important, is that, if you could back up too, is that the terminal velocity of these 2-meter balls are coming in at less than 60 miles an hour, coming in from space, which is pretty extraordinary. So I'll conclude by simply saying the problem is huge. It's the future of humanity. It's literally how can we keep our prosperity going, how can we ensure our survival long term, and how can we make the human race a multiplanetary species. Asteroids are the low-hanging fruit of the solar system, and the technology is not impossible. It's on the edge of doable, and why it's a perfect solve for X story. Thank you.